Hi everybody, let's talk about orbital diagrams. So basically another way of representing these electron configurations that allows us to see just a little bit more whenever we practice. So we are going to represent orbitals as a line, like you can see right here, or a box. And I think you'll likely pick the line more often than not because it's easier to write than the box, very simply. So remember that in an s orbital, there is one orbital, or in an s sublevel, I should say, there's one orbital, so we draw one line. In any p sublevel, there are three orbitals, so we would draw three lines. In a d sublevel, there are five, and in an f, there are seven. And as a reminder, if you want, you could put in those m sub l quantum numbers here. You don't need to, but remember, this one is the -1 orbital, this is the 0, this is the 1. This is -2, -1, 0, 1, and 2. So those quantum numbers predict how many of those orbitals there are going to be. Now, remember, there are some rules that we need to follow whenever we fill in those orbitals. The first rule to follow is the off-ball principle. So remember, we're going to add to the lowest energy orbitals. We're going to start at the first energy level as we are adding. We're also going to follow the Pauli exclusion principle, which states that we're going to have electrons of opposite spins, so one up, one down. You'll notice that I've drawn arrows here. As you get into the hang of this, you may want to draw half arrows like this, just because it's a little bit quicker, a little bit easier to draw in those arrows. And we're also going to follow Hund's rules. So Hund's rule, remember, says that you can't have two electrons occupying one orbital if there are unfilled orbitals on the same sublevel. So for instance, we want to have all of our electrons spread out into their own orbital as opposed to putting two electrons in one orbital when there's one that's empty over here. Remember the analogy of moving into a house, right? If you have 3 bedrooms for the kids, everyone's going to want their own. If there are 3 kids, you're not going to pair up until there are 4 kids or more where you can't have your own room. Remember that there's also shorthand notation, so we can do the exact same thing we did before, where we write the noble gas in brackets, and then continue from there. So let's get some practice with this. You guys have some questions on your note guide. I'm going to join you on the periodic table. First off, we're given some information about boron, that its electron configuration is 1s2, 2s2, 2p1. So let's rewrite that, but I'm going to do letter C first. I can actually draw out this orbital notation. So if the electron configuration is 1s2, instead of writing out the 2 for 1s, I'm simply going to draw the 1s orbital and draw in 2 electrons. And I'll just make these a different color so we can see them better. We also know that there is a 2s sublevel in boron. It is also completely filled with its electrons. And there's a 2p sublevel. Notice that the orbitals are there, even though only one of them is actually occupied, and it's only occupied by a single electron. So there's your 2p1. So, in response to letter A, how many electrons are present? Well, there are 5, and we have multiple ways of answering that. Number 1, you see 5 arrows, so there are your 5 electrons. Number 2, the atomic number of boron is 5. That means it has 5 protons. If it has 5 positive things, it must have 5 negative things to cancel those out. So for both those reasons, we have 5 electrons in a neutral atom of boron. What is boron's atomic number? We just talked about that. It is 5. We've already drawn its orbital notation, and how many unpaired electrons are present? Notice when you draw out orbital notation, it's really obvious to see paired and unpaired electrons. There's your 1 unpaired electron for boron. All right, let's do similarly, but let's do it for fluorine. So I'm actually not going to erase my sublevels here because you'll notice that fluorine is also in the 2p sublevel. It just happens to be a little bit further along. It happens to have 5 electrons. So let's picture how these electrons are going to fill in, right, to get to that atomic number of 9. So as we fill in those electrons, here's our first 2 electrons. Here are our second 2 electrons. We're up to 4 electrons. Now we have to fill these according to Hund's rule, right? So we are going to fill 1 electron there. There's our 5th electron. Here's 6. Here's 7. And now we can come back and we can start doubling up, 8 and 9. So there are 9 electrons in fluorine. You'll notice for question B, how many of its p orbitals are filled? Well, here are its p orbitals. It only has the 2p sublevel. and 2 of those p orbitals are filled. So 2 are filled, and we've already drawn the orbital notation, so we are good to go. If we were asked how many are unfilled, we would say, well, there's 1 unfilled or 1 unpaired